Okay, good afternoon everyone. So this afternoon we will tackle about topics in basic calculus for fourth quarter. This is all about problems and solutions for integration. So we have here theorem 10. If f is an antiderivative of f on the open interval I, then every antiderivative of f on I is referring actually to the open interval. Is given by f of x plus c, where c is an arbitrary constant, because as what we observe, that the antiderivative is the process of finding, or it is the reverse process of finding the derivative. Okay, so as we could always, or if we are going to remember always, no, that when we get the derivative of the function, of course, in the constant part it will become 0, but for the derivative or integral, we are trying to recover the constant that has been what become 0 from the derivative, no. So we have here terminologies, annotations. Anti-differentiation is the process of finding the antiderivative, no. The symbol, that one, is also called the integral sign, denotes the operation of anti-differentiation. Then the function f is called the integrand, meaning that function after the symbol integral sign is the integrand. Then if we have here f is an antiderivative of f, we write integral of f of x dx is equal to f of x plus c, as we get, as we use the operation for integrand. The symbol that one and dx go hand in hand. Dx help us identify the variable of integration. So depending on the variable of integration, example, if after the integrand, no, or the quantity after the integral sign is written as dt, so therefore with respect to t, no, that variable, the expression f of x plus c is called the general antiderivative of f. Meanwhile, each antiderivative of f is called a particular antiderivative of the function f. Okay? So we have here some illustrative example. Determine the antiderivatives of the following functions. We have here number 1, integral of tx over x cubed. So this one is about rational function. Okay. Second, we have integral of x cubed, or integral of cube root of x rather, dx. Then the third one, we have here integral of 1 over 8x minus 4 dx. Okay, let us begin with example number 1. We have here the solution for number 1. But first, let us have our formula in getting the antiderivative of the function. Okay, so we have the formula integral of x raised to the power of n dx. So all we have to do is we will add 1 from to the numerator, or to the exponent of the numerator, and whatever that we observe from the numerator, or the exponent of the numerator, will be also our denominator. So we have n plus 1, and as we observe also that we have the denominator of n plus 1 also, then plus c. Okay, solution for number 1, we have integral of dx over x cubed. Actually, if you're going to apply this formula above, okay, from the problem integral of dx over x cubed, we have to rewrite the function 1 over x cubed into integral of x raised to the power of negative 3 dx. So if you could still remember about the laws of exponent for negative. Okay, then after that, we can now apply the formula. We have integral of x raised to the power of n dx. So we have here, by adding 1 to the power of x, which is negative 3, we have negative 3 plus 1, and also the denominator, we have negative 3 plus 1, then plus c. Okay, then simplifying, we have here x raised to the power of negative 2, because negative 3 plus 1 is negative 2. Then also in our denominator, we have negative 3 plus 1 become negative 2 plus c. Okay, then finally, we have here 1 over, because that one is negative exponent, having a negative exponent. So we will have to rewrite that one, considering that this x raised to the power of negative 2 become negative 2x raised to the power of positive 2. Okay, we applied at this point using the laws of exponent for negative. Then for the solution, number 2, integral of cube root of x dx, we will also rewrite this equivalent function as integral of x raised to the power of 1/3 dx. That one is referring to rational exponent, okay? Because we have here x cube of, we have cube root of x rather. So if we're going to rewrite that one into rational exponent, it is actually equivalent to integral of x raised to the power of 1/3 dx. So we are now ready to use the formula in getting the antiderivative of the function by adding 1 to the exponent and also from the denominator. So we have here, from that, it will become x raised to the power of 1/3 plus 1 over 1/3 plus 1. Then we have plus c. Okay? Then we simplify. We have here 1/3 plus 1 become 4 over 3 as the exponent of x over 4 over 3 plus c. Then we have here a fraction from the denominator. So we have to get the reciprocal of 4 over 3 and multiply it to the base of x raised to the power of 4 over 3. So it will become 3 over 4 x raised to the power of 4 over 3 plus c as our final answer for number 2. Then the solution for number 3, we have here integral of 1 over 8x minus 4 dx. So this type of function, we are not going also to use the formula, okay, that is being presented from the previous slide, because this one is we'll have to use the properties of logarithm, okay. So at this time, we will have to let as our value of u, no? Then after that, we will have to get its corresponding derivative. So we let u be equal to 8x minus 4. Then of course, if we're going to get the derivative of this function, become derivative of u is du. Then derivative of 8x minus 4 is 8 dx because that variable is x. So we write dx. Finding the value of dx become du over 8. Then using now, because our u is 8x minus 4, then therefore, because our u, we let that one as 8x minus 4, so we have integral of 1 over u. Then we already have the value of our dx, which is du over 8. So we just multiply by replacing the value of dx, which is du over 8. So we can now factor out 1 over 8. Then we have here integral of 1 over u du. Then this time, note that integral of 1 over u du is equal to ln of u plus c. So actually we use at this time the property of logarithm. Because if you're going to rewrite this given function into negative exponent, then applying the concept of or the formula for getting the antiderivative, the function becomes 0 or the function becomes 1 because it has a power of 0. So that's why we have to use the logarithm property. Then from that, it will become 1 over 8 ln of u plus c. Then substituting the value of u, which is 8x minus 4 plus c. So this one is our final answer for integral of 1 over 8x minus 4 dx. Next, we have here another part of our the problem. So we have here use substitution principle to find the antiderivative of the following. Number 1, we have integral of 5x times square root of 1 plus 4x squared dx. So in this type of problem, of course, the substitution principle can be applied, in which we have to decide what quantities that we are going to let as our value of u. Then after that, the things that we need also to consider in identifying the value of u is that when we get the derivative of u, there are terms that can be cancelled out. So, like for example, from this one, integral of 5x times square root of 1 plus 4x squared dx, if we let as u, which is 5x, then if we're going to get the derivative, that is 5. And it will not make sense at all because there is no quantity that will be eliminated. So, if we let u be equal to 1 plus 4x squared, so we have here, as we get the derivative, it will become 8x. Then, of course, the variable x will be cancelled out. So, there will be the quantity that can be cancelled out when our u is equal to 1 plus 4x squared dx. So we have here, we let u be equal to 1 plus 4x squared. Then derivative of u is 8x dx. Finding the value of dx become du over 8x. Then we have to substitute the value of u, okay? Or as we let that one as u, which is 1 plus 4x squared. So become integral of 5x times u raised to the power of 1 half. Okay, because square root is 1 half. Then we are going to rewrite that one into rational exponent. Then we have multiplied by du over 8x. As what we observe, we have here 5x and 8x. X will be, or variable x will be cancelled out. So we can now factor out 5 over 8 times integral of u raised to the power 1 half the du. Then this part, we can now apply the formula for getting the antiderivative of this function by adding 1 to the exponent and also from the denominator. So become 5 over 8 times the quantity of u raised to the power of 1 half plus 1. And also from the denominator, we have 1 half plus 1. Then we have plus c. Simplifying, we have here 5 over 8 raised to the power of 5 over 8 times u raised to the power of 3 over 2 because 1 half plus 1 is 3 over 2. Also same as in the denominator. Then we have plus c. Then after that, we have here to, we will now simplify by getting the reciprocal of 3 over 2, then multiplying it to the base of u. So we have 5 over 8 times 2/3 of u raised to the power of 3 over 2 plus c. Simplifying, we have here 5 over 4 times 1 over 3 because 2 and 8, okay, we can actually get their lowest term. So we have 5 over 4 times 1/3 u raised to the power of 3 over 2 plus c. Finally, we have here by replacing the value of u or substituting the value of u, which is 1 plus 4x squared, become 5 over 12 times the quantity of 1 plus 4x squared raised to the power of 3 over 2 plus c. So that will be our answer for example number 1. Okay, we have here example number 2. Integral of x times square root of x minus 1. So this one, whenever we use as our value of u, which is x minus 1 or x, there will be no quantity at all that can be cancelled out. No? So at this time, we let u be equal to x minus 1. Du is equal to dx, of course. Then getting the value of x, we have here u plus 1. So this is now the time that we will have to replace x as u plus 1. So we have here integral of u plus 1 times u raised to the power of 1 half as our x minus 1. Then we have times du. Then multiplying that one to each term, we have u times u raised to the power of 1 half become u to the power of 1 half plus 1 half plus 1 plus u raised to the power of 1 half because we multiplied it by 1. Next, we have here simplifying, we get u raised to the power of 3 over 2 plus u raised to the power of 1 half du. Applying the concept, no, using the formula for integral, we added 1 to the exponent. So we have u raised to the power of 3 over 2 plus 1 over 3 over 2 plus 1. In the other side, we also added 1. No? So we have u raised to the power of 1 half plus 1 over 1 half plus 1 plus c. Simplifying, we get u raised to the power of 5 over 2 over 5 over 2 plus u raised to the power of 3 over 2 over 3 over 2 plus c. Getting the what? The reciprocal of 5 over 2 and 3 over 2 and multiplying it to its base. We have here 2 over 5 u raised to the power of 5 over 2 plus 2/3 times u raised to the power of 3 over 2 plus c. Then we know that our value of u is, we have x minus 1. So we have here 2 over 5 of the quantity x minus 1 raised to the power of 5 over 2 plus 2/3 times x minus 1 raised to the power of 3 over 2 plus c. So that will be our answer for solution number 2. We also have here integrals yielding inverse trigonometric functions. The following are integrals that lead to inverse trigonometric functions. So we have the first property, integral of dx over square root of a squared minus x squared. This one is equivalent to the inverse trigonometric functions of arc sine of x over a plus c, where a is greater than 0. Another one, for the second property, integral of dx over a squared plus x squared. That is actually equivalent to an inverse trigonometric function of 1 over a arctan of x over a plus c, where a is not equal to 0. Next, we have here integral of dx over x times square root of x squared minus a squared is equal to 1 over a arc second of x over a plus c, where a must be greater than 0. In general, if u is differentiable function of x, then integral of du over square root of a squared minus u squared is equal to arc sine of u over a plus c, where a is greater than 0. Next to that, we have here integral of du over a squared plus u squared is equal to 1 over a arctan of u over a plus c, where a is not equal to 0. The last one, we have integral of du over u times square root of u squared minus a squared is equivalent to 1 over a arc second of u over a plus c, where a is greater than 0. So we will apply all this concept or properties by some of the problems given. So we have here, evaluate the following indefinite integrals. Number 1, integral of dx over x times square root of x squared minus 16. Okay, solution for that one, of course, we have from that one, integral of dx over x times square root of x squared minus 16. We will rewrite it into integral of dx over x times square root of x squared minus 4 raised to the power of 2. So we simplified 16 as 4 raised to the power of 2. So that we can now apply this property, which is integral of dx over x raised to the power of x squared minus a squared, wherein that is actually equivalent to 1 over a arc second of x over a plus c, where a is greater than 0. So from that, it will become 1 over 4 arc second of x over 4 plus c as our final answer for number 1. Let us proceed now to example number 2, integral of dx over 4 plus x squared. Of course, from that, we will also rewrite that one into, we have here integral of dx over 2 squared plus x squared, because 4 is actually equivalent to 2 raised to the power of 2, which is 4, of course. No? Then we can now apply this property. Integral of du over a squared plus u squared is equal to 1 over a arctan of u over a plus c, where a is not equal to 0. Then after that, we can now apply. So that is actually equivalent to, okay, 1 over 2, no? 1 over 2 arctan of x over 2 plus c as our final answer. Okay, so we have here, we will proceed now to the application of the integral. This is what we call as the exponential growth law and the exponential decay law. Some quantities grow or decay at a rate proportional to their size. This relationship can be written using the differential equation. Okay, so we have here this one, because we are dealing with this the type of problem wherein there is what we call as an increase in population and decrease of the population. The size that is being described in this given scenario is referring to the population. So we have here dy over dt is equal to ky, which can be solved using the general function y of t is equal to y of 0 times e raised to the power of k times t. So let us have now our proof on how we get this y of t is equal to y of 0 times e raised to the power of k times t. So from that, dy over dt is equal to ky. We can actually separate variables, no? So by multiplying 1 over y to both sides. So it will become dy over dt times 1 over y is equal to ky times 1 over y. Simplifying, we get 1 over dy, 1 over y times dy over dt is equal to k. Then we can actually multiply dt to the other side, so become 1 over y dy is equal to k times dt. Then, we can now get the integral of both sides. Integral of 1 over y dy and integral of k times dt. Then, of course, we will have to use the properties of logarithm for 1 over y. So, it will become ln of y is equal to k times t plus c. Because that t is referring to the variable of integration, kanang t. So, we multiply it by k because k is referring to constant also. So, we can now get the value of y by using the property of Euler number. So we have here also for the logarithm, y of t is equal to e raised to the power of kt plus c. Or, of course, we can write it into y of t is equal to e raised to the power of c times e raised to the power of kt. Because when we multiply those quantity having same base, we will add their exponent. So we can actually factor them into e raised to the power of c times e raised to the power of k times t. After that, when t is equal to 0, so we have y of 0 is equal to e raised to the power of c times e raised to the power of k times 0. Then, after that, we can have now y of 0 is equal to e raised to the power of c times e raised to the power of 0, or y of 0 is equal to e raised to the power of c, because that Euler number to the power of 0 become 1. So, multiply it by e raised to the power of c become e raised to the power of c. Simplifying, substituting that one from the original equation, it will become y of t is equal to y of 0, wherein it refers to the initial population, times e raised to the power of k times t. So let us now proceed to some example, illustrative example for this type of problem. Consider a colony or a group of bacteria that is observed to grow at a rate that is proportional to the number of cells present. At the start, there are 8,000 cells. After 2 hours, it increased to 14,000. How many there will be after, or how many bacteria there will be on after 1 day if the growth rate is constant? So meaning for 1 day there are actually 24 hours. So that is what we are going to identify. No? How many bacteria will there be after 24 hours? So of course, let us have now the given y of t. We know that our initial population with t is equal to 0 is 8,000, no? As being described in the problem, no? At the start. So we have y of 0 is equal to 8,000, or y of t is equal to 8,000 times e raised to the power of k times t. After that, of course, with t also is equal to 2, then with y of, also we have here y of t, or y of 2 is equal to 14,000. What was about after 2 hours, no? That is actually being described in the problem. After 2 hours, it increased to 14,000. Then, next to that, we have here 14,000 is equal to 8,000 times e raised to the power of k times 2. This time also is we'll have to get the value of k, no? After that, we can have, or we can divide both sides by 8,000. So we have e times e raised to the power of 2k, or k times 2 is 1.7. 1.75, because 14,000 divided by 8,000 become 1.75. Then, using the property of logarithm, become 2k is equal to ln of 1.75. Dividing both sides by 2, we can now have the value of k as 0.2798. Then, when t is equal to 24 hours, because that is what our goal in this problem, that we have to identify the number of bacteria after 24 hours. So we have here y of 24 is equal to 8,000 times e, wherein our k is actually equivalent to 0.2798. We have e raised to the power of 0.2798 times 24, referring to our t, which is 24, or 1 day. Simplifying, we get 24, y of 24 is equal to 600, 6,598,790. That is not cells, that is actually bacteria. So that is the number of bacteria after 1 day. Let us now proceed to example number 2. Consider the constant rate of decrease of a certain microorganism. So this is decay. This is type of problem, or the decay type of problem. At the start, there are 12,000 microorganisms in a certain place. After 30 seconds, the population decreased to 8,000. If the number of microorganisms is directly proportional to the constant rate of decay, and such decrease in number continues at the same rate, then how many microorganisms will there be after 45 seconds? So, as what we observed, that our initial population is 12,000. Then after 30 seconds, it will decrease, no? Or it decreases to 8,000. So we are going to try, or we are going to find out how many microorganisms will be left after 45 seconds. So of course, the given, we have y of t is equal to 12,000 times e raised to the power of k times t, where y of 0, or our initial population, is 12,000 as being described in the problem. Then after that, when after 30 seconds, the bacteria become 8,000. So we have 8,000 is equal to 12,000 times e raised to the power of k times 30. Dividing both sides by 12,000, we have here e raised to the power of 30k is equal to 8,000 over 12,000. Then simplifying, we get 30k. Using the properties also of logarithm, we have ln of 2 over 3. No? Then finding the value of k, we have here negative 0.0135 as the value of our constant. No? Then after that, we can now use this given quantity to identify the number of microorganisms left after 45 seconds. So we have y of, that is not y of 24 actually, that is y of 45 rather. So y of 45 is equal to 12,000 e raised to the power of negative 0.0135 times t, where t is equal to 45 seconds. So y of 45, that is not, again, that is not 24, that is 45. So we have y of 45 is equal to 12,000 times e raised to the power of negative 0.0135 raised to times 45 also. Simplifying, we get y of 45. No, after 45 seconds, we have here 6,537 microorganisms left. Okay, so as what we observed, from 12,000, it decreased to 8,000, and after 45 seconds, it also decreased to 6,537. Okay, so I hope that this will help you in answering your problem, particularly in encountering those problems which are similar to your activity. Okay.